upside down again. Metamorphic structures. Metamorphic and structures. This is good coffee. Geologic structures can be related to one another and help accommodate a deformation. Faults, folds, and shear zones. As a hinge is formed, faults can develop along to accommodate the tension. So like this is basically all of these joints are being formed along this hinge to kind of accommodate its shape. You know, like it's being pushed together, but it's, you know, more brittle material, so it's like creating joints along that, you know, and that's kind of how this forms like there. Joints and folds can be caused due to the force created by a fault. Some faults and joints could imply the fault is nearby. So there's a fault right here, and it stops right there, and then these are like, you know, like little joints, little breaks in the rock that indicate like, oh well, they're all pointing this way. Maybe something happened down here. Maybe there's some kind of great amount of force, and that could have been caused by a fault. It's also a monocline, so we definitely know that there's some kind of, you know, movement down at the surface, at the subsurface. So near the surface, faults are brittle and move along the fault, but at depth, the high temperature allows for a more viscous movement so that the force is spread over an area and causes a shear. So this is saying like at the surface everything's brittle, so it's going to break. But deep down, you know, at their surface, everything's a little bit more liquid, so when something moves, you know, like fault hits, you know, at the bottom, it's not just going to like break everything unless it's like a huge amount of force. It could, you know, more likely it's going to kind of spread out and create like smaller movements, spread all of its energy and its force, and like instead of being confined into this one movement, it's going to kind of spread out and kind of shift stuff around. As layered rocks are pushed up, they may be forced to fold to accommodate the new geometry caused by the fault. So yeah, this is basically just something moving on top. You know, it's like going, oh hey, I'm gonna go ahead and I'm gonna go ahead and move up. Oh, I'm too heavy. And then it just kind of, you know, folds like that, you know, falling in on its own weight and just kind of causing new geometry. It's a thrust fault. Anticline, syncline, basically saying like it goes up, syncline, comes down, kind of goes like that. Cleavage is typically parallel to axial surface of folds and forms at the same time. So right here we're kind of predicting out where this goes, right? Like let's say this is at the surface and this is eroded away. We're saying that, oh well, this layer goes up and it must come down. That's why the dotted lines are there. You know, I think it was the last video that I talked a little while ago about like what these symbols mean. But yep, and this cleavage, these little dash lines are the cleavage, and they're parallel to the actual surface, which here's the axis, and that means this is the actual surface. So if you kind of shifted this drawing around, right, like if you if you shifted it down, then the cleavage should be going straight at you. But here you see like it's just going in the same plane as the actual surface. Movement of faults can alter the way the rock may metamorphose by having igneous rocks cool faster, or by burying some rocks and altering the way it may metamorphose. So basically just saying like if you move stuff around in a system that has heat and pressure, that because it's changing position and changing, you know, like the amount of pressure and heat that's on it, it won't metamorphose the same way. I'm trucking along. I'm doing pretty good. Occurrence of deformation and metamorphism along shear zones. Occurrence of deformation and metamorphism along shear zones. Okay. Features on fault zones. Most faults have intense fracturing with crushed rocks. So this is kind of like brecciation. You know, most rocks have intense fracturing with crushed rocks. Smooth, polished surfaces indicate movement direction. This features and fault zones, yeah. So some features may curve as they are lagging behind the movement. So this is like, it goes like, let's say like these ones are going straight up and down, right? And then they just kind of curve along, you know, like as this moves up, it's just kind of shifting all of this stuff. I think I may have colored these wrong. This is supposed to be moving up, and that one's supposed to be moving down. Metamorphic shear zone features. Displacement, which is just, you know, again, moving from here to here. Deformation, which is, you know, stuff that was like this, that gets like all squiggly and undefined. Metamorphism, crystals change, you know, from like one material to another due to heat and movement. How and where do structure slip faults form? Rocks undergo stress that shear two directions, displacing a section of the unit. This can happen in the upper crust or at depth. All transform boundaries are strike-slip faults. Most are boundaries between two oceanic plates. So this is basically just saying strike-slip faults are like when something is just kind of moved in relation. It's nothing's going on top or beneath something. It's just kind of shifting back and forth, and that it mostly happens, you know, the transform boundaries are strike-slip faults. So like between Africa and South America, there's a big plate boundary that is that's a huge strike-slip fault. And some mountains and hills form where strike-slip faults changes directions. The change causes the material to bulge and bend to accommodate the force. So like this is saying like, oh, it's shifting this way, but there's a bend in it, so then it's going to create little mountains right here. This is a bird's eye view. So this would be like something shifting that direction and the other one's moving this way, so it's kind of like it's kind of like, you know, if I'm pushing up with this hand and down with this hand, it's creating like that, right? Well, right here in this zone, in that area of bend, a lot of the material is going to clump together. Like if you move a piece of fabric, right, it like clumps together. That's a terrible example, but it like clumps together, and it would push the material up into a different area. Oh man, messed up again. Oh no, I think I got all the information though. Yeah. Transformations. How original location, orientation, shape, color, and size of the volume of rock has changed. So basically just transforming from this shape to this shape. It just moves stuff around. Translation changes in position, so it just goes to the right. Rotation changes in orientation. This one's just kind of rotating up. You can see it as rotating up and moving to the right, which means its rotation is, you know, let's say that this piece goes up, so its rotation is clockwise and its translation is to the right. Dilation is the change in spacing, so like these are 1 inch apart, now they're 3 inches apart because they've been dilated. Distortion changes the shape. Okay, pretty, yep. Of course, more than one of these changes can happen at any given time. Two types of responses to force is rigid, which means like it's moved with where it's intact with no change. So it's like if it's a rigid translation, like a rigid transformation, then it just moves the rock. But if it's non-rigid, which means that it can flow, then it's like the same type of material moving but also shifting the material around. There it is again. Where am I at? 16? Okay. Displacement. Shortest distance from initial to the final position. So again, just moving from one place to another. Displacement vector represents the length and magnitude and direction of that line. So this is a vector, a displacement vector. It's saying like, oh, it was a big movement and it went in that direction. Displacement field is a whole field of vectors, so basically just a bunch of vectors that represent the total displacement. So it's like, oh, well, this particle moved like this particle moved like that one moved like this. Kinematics is focusing on how and where where the vectors moved. It does not focus on the forces that were applied, just on the motion of the material. Yep. So displacement vectors again. Deformation path is basically like, oh, well, this is how it moved from one area to another. This is just, when you're looking at a surface, you're just going to know the vector usually. You're just going to say, oh, well, it started here and now it's here. So it went like that. Deformation path, you could gain that, but it's like saying, oh, first it went down and then went up and then went down again and now it's here. But both of these are basically telling you where it started, where it ended. This is just telling you the path it took. Distance is measured along the deformation path. So you can't measure distance along a displacement vector because it's like, oh, well, this is 1 meter. Well, this is also 1 meter from this point to this point, but it moved down and up and down and up, so maybe it moved 1.6 meters. Paths have a number of possibilities. So this is just particle 1, particle 2, 3, and 4, and like they got kind of squished together, and then particle 1 stayed, particle 2 went up a little, particle 3 and 4 went up in the same space, particle 1's in the same position. You know, it's basically just showing you how they changed in relation. These are the deformation paths. This can have verticals whenever you were analyzing a body while it was in motion. Yeah, it's easy to do if you can see it while it's happening. Harder to do after it's happened. This is just more stuff on deformation paths. Deformation path of a shaded area through time, so it's just, oh, it moved and now it's like this. See, this is how it started, then it got shifted down, and it got kind of pushed up, and it got kind of moved around, and now it's all squiggly. 10 million years, 3 to 1 million today. So this is like analogous to a flock of birds. Like they start like this, and then they, you know, as they fly, they all change position, and then they end up in a reverse V formation. Like the aggregate is the shape of a flock, and each bird is a vector point. So like the aggregate would be like the total shape, and each bird is just like a point in space in which that is shifting. The general movement may be relevant in finding the path than focusing on a single point. So in general, it's good sometimes to just focus on the entirety, the aggregate as a whole, instead of just like this bird. Well, this bird is here and it's here. Say it stayed in the same position, but like this bird, right? It moved forward and then it moved all the way back. So, you know, it's better to look at the whole thing instead of just saying like, oh, well, it went forwards and backwards, you know, but this one didn't go forwards and backwards at all. So if you know, just kind of deciding what to focus on. It aims in the direction, steers towards average position, and will attempt to avoid collision. This is, you know, like the formation of birds, and kind of the same thing with particles, is that they aim in a general direction and they start towards an average position, and they'll attempt to avoid, you know, colliding into one another. Applied example, hot spots. A hot spot is basically like a position in which, a place in which like a magma chute goes all the way to the surface past the crust, forming an island arc, kind of like Hawaii, and then as the crust shifts, the hot spot, you know, puts more material in different areas, and you can kind of tell like the direction that it went because of where all the material is located. Man, I don't know how teachers do this. This is exhausting talking about this so long, but I want to, so I'm going to. Translation. Change in position. This is seen most clearly in a pure rigid body. Oh, yeah. So a translation is basically like right here. So like that point that I'm kind of generally pointed at is saying that, there we go, I found my phone, is saying that in a rigid body all the deformation paths are the same, so it's just a solid body that shifts, right? So the deformation paths are just saying like, oh, you know, like the translation is just left to right or right to left or whatever. displacement vectors, the distance of transport can be in millimeters or in thousands of kilometers. So it's basically like, it could be just, oh, it moved literally this far, or oh, it moved tens of thousands of miles away. Like, who knows? Just kind of depends. Direction, exposed as trend and plunge. So trend and plunge is kind of like strike and dip, just a little bit different. I think we'll go over that later. We'll go over it right now. Trend and plunge. Trend is the azimuth from 0 to 360 of strike movement, and plunge is the dip of the movement. So trend is basically like what actual cardinal direction does it face, and plunge is basically the dip. Basically that's what trend and plunge is applicable when talking about movement. Sense of transport varying in relation to the movement. So this one is the movement was southeast. Yeah, so that's I kind of like trend and plunge a lot better. DVDP, here's the deformation path is unknown. Here the stone is flipped. Okay, so yeah. So again, dash marks means like we know that it started here and that we're not sure about what happened right here, but we know that the stone took that path from here to here. So like for 10 million years we have no idea what happened, but in 1 million years we know it did this. So the displacement vector and displacement path is usually most likely that they are different. It's usually like, it's basically, this section of the notes is saying like this would be like a purely rigid movement transportation, and this is like more likely what happens in nature. Oh, I'm getting close to 20 pages. Translation, slip and fault. Net slip, displacement vector that connects the x, y, and z to the x prime, y prime, and z prime of two reference points. So right here, this would be an oblique slip, right? Yep, it's an oblique slip. It doesn't go with the strike, it doesn't go with the dip, it goes kind of at an angle, portions of each. So like, it's like, oh, well, it's 35 degrees down from where it would be if it went from the strike. And so that's the 60, 50, southeast. So 35 degrees from 90 would be like, so like, yeah. Here we see a block that has moved in an oblique angle on a normal fault. The southeast block moved down in relation to the northwest block. The faults accommodates a left-handed movement. Okay, that's going to be... Am I talking about left and right-hand movements? I don't know if I am. So basically, a left-handed movement, I'll just explain it real quick, is like if I'm standing on this block, this is the B block, and I'm looking at the A block has moved to the left. So up and to the left, which means like if you're standing on the A block looking at the B block, it would have moved down and to the left. Like just depends on where you're viewing it from, but either side you see that it has the material that you're looking at from the reference material has moved to the left. So this is just, I think it's just some basic trigonometry. Yeah, right here. It's on the left wall. So this is saying like right here, this is that 35 degree dip. 40.1 centimeters. So we know that this is referencing like this pebble that broke, and that the pebble went from here to here. And so the net slip component, the dip slip component, so that's saying that this is along the dip, this is along the slip, and this is the strike, or this is along the strike, this is along the dip, and this is the total. So along trend, so the trend goes along with the strike, kind of along plunge is basically the dip, and right here is the net slip that we're looking for. So it's just basically some basic trigonometry. SOHCAHTOA, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Or a squared plus b squared equals c squared. So this is just to find the net slip. And you can find it with, if you have measurements, one of these measurements, you can basically find the net slip pretty easily. It's not too hard. and this is the trend and plunge. Like right here, the 60 is the 6 degrees northeast. You know, it's not quite at 90, so it's not northeast purely. It's just kind of, you know, northeast, and the 50 is the angle that it's going down. Yeah, this is the angle of the dip, I believe. And this is the difference is this is the angle of the dip, and this is the angle that, like, the position that the blocks moved in relation to each other, if that makes sense. Like, this is how far something dips down towards the center of the earth, and this is just how much difference it is from the original position to the new position that it's moved. Oh, please tell me I have all the information. Yeah, that'll work. Okay, so the instabilities of rigid and non-rigid deformities. Okay, so rigid again was just all the vectors are moving in the same place. Non-rigid means like it's kind of wonky and different. Non-rigid versus rigid is scale dependent. So from close up, this single fault can be considered to be rigid due to all of the deformation vectors and the deformation pathways. So that's saying, like, if you're looking at something really close up and everything's just kind of shifted a little bit and everything's kind of shifted, then it's like, oh, this is rigid. But then if you zoom way out to a macro scale, like over an entire field, then those rigid deformities kind of change a little bit, and then it would look non-rigid. So when you're considering if something is rigid or non-rigid, you have to include the scale in which that you're looking at. So at, you know, 0.1 meters, it's rigid, everything's the same. But at, you know, at a scale of like 10 to 100 meter scale, then those little 0.1 meter movements add up to kind of shifting and moving. From a distance, we see faults are more penetrative, and the deformation is non-rigid body. A penetrative structure must be spaced so closely that they appear to be everywhere in the non-rigid body. So right here, like, they appear to be everywhere, but, you know, they go through the entire thing. There's no space here where there's nothing going on. It's all kind of connected. And they penetrate the entire area of the formation. The difference in non and rigid bodies depends on the degree to which structures are penetrative. And did it slip or did it flow? This again is kind of, I think, scale referenced as well. Like, if you're looking at a microscopic scale, mostly everything slips. But if you're looking at a macroscopic scale, an entire rock unit, those tiny little slips make it look like it's flowing. So it'd be, yeah. The distinction between the two are scale dependent. In the example, the non-rigid body movement above, we see that the scale of the first example seems more penetrative. Example one looks like a slip. Let's back up further from example 2. So this is basically like an even further view. Like, this is example 1, this is example 2. Example 1 is showing like the particles look like it's slipping. Example 2 makes it look more like it's, you know, like the example 1 looks like a rigid body, example 2 looks like a non-rigid body. And then if you back way up to like the actual, like, if you're on a helicopter and you go way up in the sky, you see like it's an entire flowing area. And this little box represents where example 2 would be. And at this scale, it appears to flow. And though flows do exist, it can be hard to tell if it's a collection of slips or a true flow. So, like, sedimentary rock usually will be an accumulation of slips, unless it's been like metamorphosed, or if it's like a really low competency rock. And magmatic rocks, igneous rocks, you know, they usually have a flow because it's just one matrix as it forms. So it just kind of depends on what you're looking at and if it's really that important of a quality to, like, determine what you're studying. So I think I'm going to end video 2 right here and see how